Okay, so let's keep going with these trig functions. If you were actually to go back to the definitions and compare with right triangle trigonometry, what you learned in there, SOHCAHTOA in other words, you would actually see, maybe not at first, but you would eventually see though that these identities which hold in right triangle trigonometry carry over here. So these identities hold. What's nice about these also, if you notice, is that once you know, if you're trying to find the trig functions at an angle, theta, once you know sine of that angle, theta, and cosine, you can actually get all these trig functions. Because you can see they're all expressed in terms of sine and cosine. All right, now when we actually evaluate the trig functions of more angles to come, it turns out it's actually very useful to know where sine, cosine, and tangent are positive or not. In other words, it's useful to know in what quadrants sine is positive, cosine is positive, and tangent. Again, I know tangent is defined in terms of sine and cosine, but knowing tangent will help a bit. Now, if you remember, the quadrants look like this. This is quadrant 1, this is x, this is y. So it's 1, here's quadrant 2, here's 3, here's 4. And really, it's just by definition that in quadrant 1, all sine, cosine, tangent, all three of those are positive. Mostly because x and y are both positive. X and y being the coordinates of that point P. In quadrant 2, only sine is positive. Only sine. Because sine, remember, is the y coordinate and cosine is the x coordinate. So in 3, only tangent is positive. And in quadrant 4, only the cosine is positive. In quadrant 1, all three of those are positive. I know it's a lot to remember. That's why people have this. Way to remember it. All students take calculus. Okay? All students here take calculus. Okay, so again, that's basically telling you which of those three, sine, cosine, tangent, which ones are positive. So in quadrant 1, that's here. Okay, this is supposed to be just like the xy plane. So we have, here's quadrant 1, all of them. Here's quadrant 2, sine. That's what the S is, all students. Quadrant 3, we have tangent, T. That's the one that's positive. All students take. We have calculus, cosine. Only that one is positive. There. Okay, so now let's consider this. Let's draw now 30 degrees, okay? Well, we know what that looks like, right? In standard position, we're drawing it. Okay, so that's going to look something like this, right? We have standard position. We have this. That's the initial side. The terminal side is going to look something like this. So this here is 30 degrees. Okay, let me see if I can fit that in. Now, that's 30 degrees. Here, what I'm going to do is draw 390 degrees. Okay? Which is the same, of course, as 360 degrees plus 30 degrees. Well, how would I draw that then? Well, let's see. So we have, again, this is standard position, so the initial side is always the same. Okay, so we have the 360 degrees, right? That means we come all the way around counterclockwise. We have that extra 30 degrees. So we go up here, 30 degrees, like so. So again, here, the 360 degrees, this tells us to go all the way around, turn completely around. And then we have this 30 degree left over, which is here. Now, it might be hard to see it from the way I drew it, but if I were to draw these two angles in the same plane, the terminal sides would overlap each other. Here, let me do it. Let me see. Let me erase this. Oh. Let me erase this, and let's see that. So, erasing this. Let me show you what I mean. So I'm going to do this one in red. So 390 degrees, right? That's in red. Again, same initial side. So the initial side, they overlap. So if I draw this, we have all the way around. That's 360 degrees. We have 30 degrees remaining, so we go up 30 degrees. And now you can see that the terminal side overlaps with the 30 degrees. In other words, 30 degrees and 390 degrees, as you can see, the initial side, okay, they overlap. The terminal sides are the same as well. So we have that here. Let's do another example. Let's now draw, say, let's draw 90 degrees. Let's draw that. And then we're going to draw 450 degrees, which is 360 degrees plus 90 degrees. Okay? So what does 90 degrees look like? Well, here again, we're in standard position. Okay? Just make that a little bit nicer. Like so. We'll come back to this. Okay? So we know what 90 degrees looks like. The terminal side's going to be up here. So this is 90 degrees. Okay? Good. Now what about here, 360 plus 90 degrees? Well, it's really just like the previous example. Again, standard position. Okay? 360 degrees. Come all the way around, like so. Back where we started. Now we rotate the remaining 90 degrees. And we're up here. Now, if I were to do that same one, the same rotation here, over here, what would happen? So this is our initial side. So I'm going to rotate all the way around. That's 360 degrees. We have the 90 degrees left over. So our 450 degrees is going to look like this. But notice, I know it might be a little tricky to see, the initial side and the terminal side are the same. And the only difference was to get from 90 degrees to 450 degrees, we basically just do an extra full complete rotation. What I'm trying to get at here is the idea of two angles being coterminal. Basically, two angles in general are coterminal if their initial and terminals, if their initial sides are the same, their terminal sides are the same. The only difference really is just a rotation. And again, as we just saw, as we've seen before, in a circle, a complete rotation is 360 degrees. So if you take any angle, let me see if I can draw it here, in standard position, right? You take any angle you want. Before I was in quadrant 1, let me do this one here. Just for some variety. So let's say this was angle theta, okay? So if I were to take that angle theta, right? And let's say I now consider theta plus, I'm going to add. If I take that and rotate it an extra 360, like so, that's going to be theta plus 360 degrees. So theta and theta plus 360, they are coterminal. They are coterminal. Let me just, I guess, keep going. The only difference with radians is that instead of 360, you have 2 pi. Because 2 pi is the same as 360 degrees. Okay, good. So let me stop. Let me do another one. Let me take another angle. Say, let me do this one. So again, here's the initial side, okay? Now I'm rotating clockwise, which is this, okay? Now I don't know what this angle is. What I'm going to do is call it a letter we have not seen before, alpha. Looks kind of like a fish. It's a Greek letter, alpha. Now what if I take this angle and add 360? So we have the same starting position, initial side. So I'm going to take that angle, okay? And I'm going to rotate 360 degrees, like so. Well, I'm back where we started, okay? And this is alpha plus 360 degrees, okay? If I instead, let me see if I can fit this in here. If I instead rotate alpha, oh, it's going to get kind of nasty. Let me fit it down here. So let me do this. See if I can fit this in here. I know this video is a little long, and I'm sorry about that. But now, if I decide, let's say, to rotate, so this is alpha. If I rotate alpha, if I subtract 360, so again, I have the same initial side. The new angle I'm going to get, right? It's going to be a clockwise rotation, 360 degrees. So I'm going to be all the way around. So this is alpha minus 360 degrees. But again, these are coterminal, okay? You know, if the angle turns around 360 degrees, it's going to be pointing back in the terminal side will be pointing in the same exact direction as before. And why do we care about coterminal angles? Well, it's because really of what's down here. If two angles are coterminal, hopefully you can see from these pictures that the point P on the unit circle that they intersect would be exactly the same. In other words, if you have a trig function and evaluate it at coterminal angles, you're going to get exactly the same value.